So speaking of Canvas, let's pop over to our Canvas page and all that kind of junk. Let me pull up the syllabus in a new tab so that we can look at things. Let me also open that up quickly. Sorry for taking forever to make this work. All right, so I'm Matthew Hartman. Most of you, or not most of you, but some of you have had me before for things. Let me get this crap out of the way. Kill that. Go away, stupid menu thing. Go away to that. I don't like this at all. All right, that's as good as it's going to get. All right, so I'm Dr. Hartman. My office is across the street in Methkin 211. Office hours are Monday, Wednesday, Friday, 10 to 11, and Tuesday, Thursday, 8:30 to noon. My email address is my last name, laptop.edu. And then there's the phone number for my office. You'd be a fool to try to use it because I'm never there unless it's during my office hours, and then I'm mostly there. Emergency class disruption policy. If we have COVID-24 or whatever, the class is going to continue on Canvas and Zoom. Sign up for the emergency notification system using the link below for stuff. Course objectives for this class, we're going to go into much more detail on several of the topics that were covered in Circuits 1. Instead of spending 2 days on op amps, we're going to spend about 2 weeks. We're going to get into second order circuit analysis. So instead of RL circuits and RC circuits, we're going to look at RLC circuits, all that kind of good stuff. We are going to review steady state sinusoidal circuit analysis exactly as it was covered in Circuits 1, but then we are also going to supplement that review with additional material regarding the analysis of frequencies that are excited at multiple frequencies. And then we're going to take our knowledge of single phase steady state sinusoidal circuit analysis and apply it to 3-phase systems, which are what are actually used for power distribution in most industrialized countries. The official textbook for this class is Engineering Circuit Analysis 10th edition by Height, Kimmerly, Durbin, and some other guy who just came on for this last edition. As per usual, do not buy the textbook, and I apologize if you've already wasted your money on it. Instead, let me get out of this thing. If you go to Google and Google CAD space ULobby, this is a professor at the University of Michigan who has created a textbook along with a couple of his colleagues at other universities that is completely and utterly free to students and in a PDF version. It is a pretty good textbook in my opinion, so if you just desperately need to have a textbook for this class, this is the one that I would actually use because it's free. Don't give Barnes and Nobles or whoever the hell $300 damn for a book that you don't need. And don't know if you're aware of this, but the Bulldog bundle is an absolute scam. All right, so back to the syllabus. I think this is so many damn windows open, driving myself crazy. Disability disclosure. If you have a documented learning disability, please go to TDS and get all your paperwork and all that kind of stuff documented as soon as you can, so that you can go take your exams at the testing center as opposed to in here. As you can tell, this room is pretty full. It's in the winter quarter. People are going to be sneezing and scratching and this, that, and the other, distracting each other or distracting you guys when you're taking your tests. So if you have an option to not take the test in here, don't take the test in here. Let's see, attendance policy, normal stuff. The official policy is there. The unofficial policy is that you're adults, and if you don't want to be here, you don't have to be here. You won't do well in the class, but that's your choice. Academic honor code, boilerplate. Being a student of higher standards, you pledge to embody the principles of academic integrity. And then we have our academic misconduct policy, which is just in a long form of the honor code. With regards to behavior, as long as you're less of a jerk than I am, everything's going to go fine. Cheating, don't do it. That pisses me off. Homeworks. So there's going to be at least 16 homework assignments in this class. Might be more depending on how squirrely I feel, but definitely at least 16. Not going to be web work. They're going to be handwritten assignments and all of that kind of good stuff using standard engineering format. I see you smiling. You will regret those smiles pretty shortly. I'm going to pull up here my expected homework formatting that I want to see. This is taking a while for it to load because it's 31 pages long. It is pretty standard, normal engineering format, except that I don't want discussion because that never made any damn sense to me. You work the problem, great. So I do want to detail what I want to see. Okay. So the first, and yes, I realize I misspelled the word answer there. Stop. So I posted the assignment sheet for homework set number 1. It's already available on Canvas and all of that kind of good stuff. So the format that I'm expecting for your homework is as follows. You will put the assignment sheet in its entirety as your cover pages. It will very rarely just be a single page, okay? So you might have 3 to 5 cover pages depending on the length of the assignment. So the first several pages of this are the cover sheet, which is just literally the assignment. I put it like this so that I can just put your grades in for each problem and all that kind of stuff. And for ABET related purposes, I can easily go back and see what you made on the problems that we use for assessment. Following the cover sheets, then you have your handwritten work for problem 1. However many pages long that takes, it is what it is. So for me, for this particular problem, looks like it was 4-ish pages for problem 1. Then I have your computer work for problem 1. So I chose to use MathCAD to solve the systems and all of that kind of stuff for this particular problem. If you need to use a computer to solve the problem, I expect to see your work for that. So that will be the next thing. In this class, we are going to be using MathCAD very regularly. While there are other computer algebra tools that you guys may be familiar with, like Wolfram Alpha, all that kind of crap, I don't care about any of that. I'm expecting you to use MathCAD in this class. If you don't want to use MathCAD, you need to be aware that you're going to lose points consistently, because part of what I am assessing you on is your ability to use MathCAD in the context of this course. So it is MathCAD, or best case scenario, you have a B. Have I made myself very clear about that? All right. We're also going to be using a circuit simulation tool called LT-SPICE. We'll get into talking about that here in a couple of minutes. Anyway, after all of my work for problem 1, then we have my handwritten work for problem 2, the computer work for problem 2, handwritten work for problem 3, computer work for problem 3, etc. Yes, sir.
So that handwritten stuff, you know how you rewrote every single problem statement like A, B, C? Can we?
Fantastic question.
Paste that, or we have to rewrite that?
So let me get out of this thing right here now that we've talked about this homework formatting example and go back to this. Let me pull up the student view really quickly here. This is one of the few things that I like about Canvas. So this is what you guys can see. It may not be intuitively obvious to you, but your first homework assignment was given to you in a docx format, which means you can easily copy and paste that stuff. So you don't have to handwrite everything. I did that for all of my solutions, but I'm not going to force you guys to do it. Because it's an extra 30 to 45 minutes of work for every problem potentially. So you can just copy and paste that, and then all of your work will go on. All of your homeworks will be submitted digitally in this class. Do not give me a paper copy. I don't want it. I will lose it. I can't lose it if you turn it in online. So I'm going to look at this homework submission portal right here to show you guys something. It says that you are allowed 3 attempts. That is just in case the graders are deciding to be nice, and if you screw up the formatting, they might ask you to resubmit using the correct format and give you some points back. Realistically, you should submit 1 file that has your work for everything in the correct format, using the proper naming convention and all of that kind of stuff. I am instructing my graders to start counting off points for this literally the first time that you submit something. I will ask them if they feel like regrading things, should you make mistakes and want to correct things and all that kind of stuff. But if you have any questions about what you're about to turn in and whether you're formatting it correctly, naming it correctly, and all that kind of stuff, come ask me, because they may decide, nope, we're just going to start off with get it right or lose points. Okay. All right, so I've ranted about homework assignments. Still opening the wrong damn window. Okay. Let's see. So here, my official policy, just to be clear, is that any homework assignment submission that does not adhere to the format detailed on our Canvas page will be rejected from grading, which means the official policy is that you should receive a 0. If the graders happen to be nice and give you points, consider yourselves lucky. Late homework assignments will incur a 20% penalty for each day that they are late. I think I actually have it saying here that homeworks are due at 5. They'll be due at midnight. So I need to go back and fix that, but they'll be due at 11:59 p.m. on the date details and all that kind of stuff to give you guys a little bit more time. All right, design projects. In this class, there will be 2 to 3 design projects. They are individual assignments. I'm expecting you to detail why you made the choices that you made, so support things with math and all of that kind of good stuff, explaining why you chose particular component values and all that kind of stuff. And then you are also going to need to supplement those design projects with an LT Spice simulation of your design, showing me that what you designed actually works and satisfies the design criteria. We're going to talk about design very regularly in this class, and all of the subsequent classes that you have with me and other professors will all be related to design, because we want you to be able to practically apply the stuff that you're learning from us. Okay. Because I have had issues in the past with students not wanting to engage with the design projects, I now have a policy that failure to complete all of the design projects gives you an F in the course. So while this really is only 10% of your grade, if you don't do it, I fail you and I'll see you next quarter. Okay. You don't have to submit correct things, but you do have to submit something in order to pass the class. All right, moving on from here. There will be 4 exams in this class. Each exam will consist of a closed book / notes portion. So realistically, for exams 1 and 2, I will provide the equation sheet for you guys to use. For exams 3 and 4, I will allow you to write your own equation sheets for those 2 exams. The exams are split up into 2 portions. So there is an in-class portion where you're only allowed to use an FE approved calculator, just like you've used in engineering 221 and all that kind of good stuff. And then there's also a take-home portion of the exam, which is usually 2 to 3 problems that require the use of simulation tools or computer algebra solvers or things like that in order to work them. Part of what you are being graded on is using those computer tools correctly. I want to be clear about that. So the total grade for any one of your exams is just the sum of the in-class portion and the sum of the take-home portion added together. Okay. So you're going to get 2 grades for each test. Simply add the 2 together, and whatever you make out of 100 is your grade for that exam. All exams have a no cell phone policy. That's fairly obvious. Here we go to our weights. So homework is 20%, design projects 10%, exams 1, 2, 3, and 4 are all worth 20%, and then whichever exam you score the lowest on is reduced to half, so that it comes out to be out of 100 points total. As per usual, I don't curve or round grades, so if you want to make an A in this class, do an A level of work consistently. Syllabus changes, I don't expect anything to change other than changing that 5 p.m. to 11:59 p.m. to give you guys more time to work on your homeworks. Other than that, I don't expect anything to change. If I do decide to change things, I reserve the right to do so as long as I inform you of it, which is what this thing says. Then we have our emergency notification system stuff. Again, COVID-19 policy. This is the winter quarter, so I don't care if it's COVID, flu, or whatever. If you're sick, stay the hell away from me. I'll be so pissed off if you get me sick, just to be real clear. Counseling services. If I'm being too much of an asshole, you can go talk to these people about it, I guess. AI. All right. So in this class, realistically, you guys could potentially use ChatGPT or something like that to help you with your design projects, all that kind of stuff. So I have explicitly put here what I will allow and what I will not allow. So with regards to your design projects, you can use them for brainstorming and idea generation, helping you understand the material, helping you solve problems and all of that kind of stuff, and writing and grammar assistance, all fair game. Just literally plagiarizing a robot effectively is not acceptable, so you can't just turn in whatever ChatGPT tells you. Using it to help you during the take-home tests and all that kind of stuff is also prohibited. There we go. Here we have our tentative course schedule. So this class is effectively broken up into 4 modules, like I talked about earlier. We have a very in-depth look at op amps. Then we're going to talk about transient analysis for second-order circuits. Then we have steady-state sinusoidal analysis. And then finally, we have 3-phase circuit analysis. So the amount of material on each exam is significantly smaller than what you guys saw in circuits 1. So hopefully that translates to a better understanding of things and arguably less stress. All right, so that's the syllabus. Anybody got any questions about syllabus related stuff?
The exam is comprehensive.
No. So exam 1 is just on op amp stuff. Exam 2 is just on transient analysis stuff. Exam 3 is steady state sinusoidal circuit analysis. Exam 4, 3-phase power. Any other questions? Yes.
So on design projects, basically just would be computer simulations, not building any circuits.
Correct. You're not physically required to build anything. It will just be computer simulations and then the math behind why you chose what components you chose to get the job done in a satisfactory way. Because there's not an infinite number of ways to design all of these things, but there are several different ways. It would be prohibitively expensive for me to have a standing order for all of the parts you could possibly use to get this stuff done. Any other questions? All right. So I tried sending an email out to all of you yesterday using Canvas. I have no idea whether or not you got it because I don't get a notification like I do with Moodle. Let me turn off my email so I don't keep getting interrupted here. But in that email, I asked you specifically, let's look at it. To download and install MathCAD Prime 8 and LT Spice 17. And the links and instructions to download these programs were on Canvas. We're not going to use MathCAD today, but I'm just letting you know that we're going to use it extensively in this class. What we are going to do today is have a look at LT Spice, which is going to require me to use my here we go. So what I'm going to do here really quickly is I'm going to go back to the home page. I'm going to open up homework set number 1. We are going to simulate one of your circuits here. So I'm going to attempt to show you how to use the circuit simulation tool LT Spice in order to do things in this class, and I realize that that's not going to be conducive, so we'll have to do it this way. Sorry that my desktop is so cluttered with bullshit. Nope. All right, so this is LT Spice's front page, as it were, and I need to get rid of this thing because it's blocking you guys' access to seeing stuff. Go away, notification. All right, so this is all being recorded, and I'm mentioning that because those icons are teeny tiny and it's going to be a pain in the ass for most of you guys in the back to see things. So looking at it again on YouTube and all that kind of stuff may prove helpful. All right, so I've set up things for a new simulation. So the first thing that I'm going to do, if I'm not mistaken, is that we have some voltage sources in this circuit. So to pull up the component menu, it's this menu right here. This looks like a digital logic gate. You just click on that. This is where generic components are found. And I'm going to type in the word voltage. into this box. This is going to give me a generic voltage source. I'm just going to randomly place it here anywhere in this field. Yes. This is a free program, so that's definitely not behind a paywall. So I just started these. Oh, yeah. So new schematic. I pressed the component menu button, so it's the one that looks like a digital logic gate up here on the top, next to the diode, between the diode and the hand. And then I typed the word voltage into the search box. Okay. So this is a generic voltage source. I'm going to right click on this. So when my mouse is over the element and I right click, it's going to pull up this menu. And it allows me to put in a DC voltage, and then I can also put in a series resistance. So effectively, this DC voltage source that we have access to is a practical voltage source in as much as we can define both the voltage and the resistance of it. We are going to use a DC voltage source here, but I want to show you guys something else. So I'm going to go over to the advanced button. And we're going to look at all of the options that we have available to us. So we can have a pulsed voltage source. So this is effectively how we would make square waves, right? Except we can define the duty cycle by saying we want the pulse to last this long and then be off for this long and all of that kind of stuff. We can define the rise time, the fall time, the delay before it turns on, the total period, the number of cycles that we're pulsing, all of that kind of good stuff. So we'll use pulse voltage sources once or twice in this class. Below that, we have a sinusoidal voltage source. This is specifically using a sine wave as a reference. Just to be clear, LT Spice always uses sine waves. We can set a DC offset, the amplitude of the sinusoidal voltage, the frequency of the sinusoidal voltage measured in hertz. Delay time, I don't remember what theta is. Phi is the phase angle, and then the number of cycles that we want our sinusoidal signal to oscillate for. Then we have exponential. So we can tell it what its initial value is, what it pulses, the rise time, the time constant for the rise, the fall time, the time constant for its exponential decay, and all of that kind of good stuff. I don't remember what SFFM, some sort of modulation. We're not going to do that in this class. And then this one down here is a piecewise linear, so we can literally just construct any type of voltage signal out of linear line segments, add them all together. And in case that's wildly too tedious, we can literally just upload an Excel file and have it do it for us. On the right-hand side, we can also do AC analysis, which is something that we're going to do later in the class. So effectively, we would say that the amplitude of our voltage source is, let's say for the sake of argument, 1 volt, and let the frequency change as we look at things. And we'll talk about that more when we get to frequency response. And then down here, we have the parasitic properties of the voltage source, so we can change the series resistance as well as the parallel parasitic capacitance. So this one voltage source can be used for tons and tons of different things. For this particular circuit, we're dealing with a DC circuit. So I'm simply going to hit cancel and go back to the DC value. I believe it was 10 volts. No, 30 volts. I'm doing the one on the bottom left. So we just put 30 in. We don't worry about the volts because it's a voltage source. It knows that the units are expressed in volts. If we wanted millivolts, we would put M. If we wanted kilovolts, we would put K. If we wanted megavolts, we would have to put MEG. Because if you put M anything, it will treat it as milli. And so you have to explicitly say meg for 10 to the 6. All right, so we have our 30 volt source here. Oh, that says piecewise linear. None. Sorry about that. So we have our 30 volt source. Now we need a resistor. Let me go back to this thing. So it looks like we need a 10 ohm resistor. So for a resistor, I can simply just take the resistor out of this menu and drop it into place. If I right click on the resistor, I can now put in its value of 10 ohms. I can also put in its tolerance percentage, right? So if I wanted to randomly give it a value plus or minus 5% to simulate a real 5% tolerance resistor, I could. I can also put in a power rating. So most of the resistors that we've used in our previous classes, we didn't really think about what power that they were designed for, but real resistors burn up if you pass too much current through them. So we can model that by changing the power rating. We're going to deal with an ideal resistor here. So let's just call it the 10 ohms and call it a day. And then I'm going to use this pencil tool to create a wire, wiring these two things together. Okay. So right now I have a 30-volt source in series with a 10 ohm resistor. Okay. I'm going to make this a little smaller and give my oops, that's not what I wanted. So give myself a little bit of room here. So I believe right here, I'm about to do this 10 ohm resistor. So when I select my resistor, it shows up in this vertical configuration. If I press Control R, it will rotate it into a horizontal configuration like we need for our schematic diagram. So I've rotated it. Now I'm just going to connect it over here and right click. And this is also a 10 ohm resistor.
I'm sorry, how did you rotate that?
Control R. Giving myself more wire over here. Let me look back at things. All right, so down this middle path, I have a current source in parallel with a resistor. So I'm just getting the wiring set up for that. All right, so for my current source, I go to my component menu and just type in the word current. By default, the direction of my current source is down. So I'm going to rotate it twice to put it in the direction up, right? I have all of the exact same options that I had for current sources as I do, or excuse me, for voltage sources as I do for my current source here. So we're just going to have a DC current source here, but once again, we could do sinusoidal, exponential, pulsed, all that kind of stuff. My memory is serving me correctly. This is a 5 amp current source, direction up. So that's what we have there. We just double check. And then that's going to be in parallel with a 10 ohm resistor. So I'm just taking a resistor, connecting it there, making it 10 ohms. I'm going to wire these bad boys together. And then I'm going to wire the bottom of my circuit like so. All right, let's go back and look here. So we have a 20 ohm resistor. And then I think it's just a resistor along this outside path. And this guy is a 20. This guy is a 10. Then I have a voltage source, which I believe is a 20 volt source that'll go up here. So when your mouse is over the normal field, if you press the delete key, it turns into a pair of scissors, and then you just cut out the thing you don't want.
What is it?
Do what? Delete. So let me double check here. So this is another 20. All right, so unless I'm missing something, and I don't believe that I am, this is effectively our circuit. We do have terminals A and B. We'll talk about those here in just a second, but I'm gonna let you guys have a moment to kind of catch up for those of you that are trying to follow along. Any questions? People largely caught up to where I'm at. I understand that this is you guys' first time doing it, so it's going to take you a little bit to figure stuff out. Not trying to be more of a jerk than usual, just tired and hungry. All right, so we can set terminals up pretty easily. So I'm just going to give myself a stub of wire out here, and then another stub of wire out here. And if we look up in our top menu, this little thing that looks like a signpost is effectively how we tell LT Spice to give a particular node a name. So I'm just going to put A. And put it over here. And I'm going to put B over here. So here are our terminals A and B for this particular circuit. Now in our homework problem, we are asked to determine the Thevenin voltage for this system seen between terminals A and B. So realistically, what we are interested in is then the voltage at node A and the voltage at node B, and the difference of those two voltages is our Thevenin voltage, right? So I want us to run a simulation. So if we go to the simulate menu and we edit our simulation command, this is a DC circuit. So I am going to do a DC operating point simulation, which is this rightmost tab. And I'm just going to drop this spice command here anywhere. It does not matter where it is. We'll just run it. And then I can either go to the simulate menu and choose run, or I can click this running man icon up here and it will run the simulation, except that it's going to give me an error. I'm just going to show you that, guys, here. So it tells us very explicitly that this circuit does not have a conduction path to ground. Please flag a node as ground. So effectively, LT Spice always uses nodal analysis to do literally everything, which means we have to tell it where a ground is. We get to choose that. So what would be a good choice for ground in this particular circuit? Any node would be okay, but I would argue that node B would be the best choice, because then whatever it tells us is going on at node A is just our Thevenin voltage. We don't have to think or do any math whatsoever, right? So I'm going to choose node B to be my ground. So this triangle thing right here is our ground symbol. And I'm just going to come over here and drop it on B. And now that's ground. If I choose the simulation command now, it pulls up this menu. So this is saying that the voltage at whatever LT Spice decided node 3 was is 17.5 volts. Whatever node 4 was is negative 12.5 volts. At A, which we explicitly identified, our voltage is 20 volts, which means our Thevenin voltage in this case is 20 volts, right? So we can be as granular or as lazy as we want with regards to defining nodes. We can let LT Spice do some. We can define all of them ourselves. I, for the most part, only define the ones that I actually care about and just let everything else be whatever it is. Okay. So it pulls up this big menu. It tells us the voltages at all of the different nodes, and then it also tells us the current flowing through each of our components. So this current I open parentheses, I1 close parentheses is the current flowing through our I1 current source. This guy right here, I open parentheses R5 is the current flowing through the resistor that was designated as R5, and so on and so forth. Yes.
Which direction?
Fantastic question. We don't really know, so we'll talk about that here in a moment. Okay, but very, very good question. So there are a couple of different-ish ways that we could potentially figure things out with regards to the direction. So now that I've closed that menu out, and of course, there's another Zoom menu in the damn way. I don't want to join audio. I want to be left the hell alone. Okay. So if I mouse over a component, so my mouse is in the middle of this resistor R2, it's tiny text down here in the bottom left, but we can see something, right? So it says that the DC operating point is I of R2 is 250 milliamps, and that there is 625 milliwatts of power being dissipated. So effectively, this diagram actually gives us all of the information that was supplied on that pop-out menu, but some more information. When we mouse over our element, it tells us the current flowing through our element, doesn't tell us the direction, and also tells us our power absorbed by this particular element. Isaiah. Yes. Walker.
I do the
All right, so go to the simulation menu, edit simulation command, DC operating point. If we mouse over a node, so instead of a particular element, now I'm just looking, I have my mouse on what's called node A. It tells me this is node A. The DC operating point voltage is 20 volts. So that information is there. If I were to mouse over this middle node, this is node N001. So this is the node that LT Spice labeled as node 1. So that if we're trying to find what any of those things that LT Spice voltage means, that's how we can do it. We just mouse over the nodes until we find what we're looking for. The voltage here is 22.5 volts. We put our mouse over our 30 volt source. The DC operating point is 250 milliamps and it is dissipating 7.5 watts. So that means it's absorbing 7.5 watts. This current source is dissipating negative 175 watts. So it is supplying 175 watts. Isaiah. It's a DC circuit. So this is what it's at. Yeah. So when we mouse over any of these things, it's telling us how much current is flowing through the element in this DC circuit. And then when we mouse over a node, it's telling us what the DC voltage with respect to ground is at that particular node. All right, so let's change our simulation command. So I'm going to delete this .op thing here. And I am going to now do a transient analysis. So a transient analysis, just to review, is just looking at what this circuit is doing as a function of time. This is a DC circuit, so we should expect effectively just straight lines in our plot. So I'm arbitrarily going to tell this to run for 1 second. It literally doesn't matter because it's a DC circuit. I'm going to leave everything else alone. And I'm just going to drop this down here. And then I'm going to run this simulation. Okay. It pulls up this graph. It's completely blank because I haven't told LT Spice what I want it to tell me is going on. So if we click on node A, so notice when our mouse is over a node, we get this probe looking thing, right? So this is like one of the leads on our multimeter. And that's exactly what it's doing. The assumption is that the other lead is at ground. So this is just going to tell us a nodal voltage. If I click on this, I get a constant 20 volts because of course I would. This is a DC circuit and we already established that its DC operating point is 20 volts. By the way, with my mouse over this node, it still tells me my DC operating point is 20 volts. So all of that information from our DC operating point analysis is there. But if we were to put our cursor over an element, now we have a current probe. And the arrow on this current probe is telling us the direction that the current is flowing, which is exactly what you were asking about, right? So getting rid of this plot thing here, because we don't actually need any of this, and just running that simulation and then mousing over, well, damn it. Okay, I guess I do need that window open. Let's just make it really small. Now I can explicitly see what direction my currents are flowing and all of that kind of good stuff if I need it. Yes, sir.
So is all of the same information that's given whenever we hover over and operating point one?
Still here.
Same.
Yep.
So this is that.
Sure. It does have that same information. It also tells you the direction and all that kind of stuff. It's cumbersome because it's going to force this plot to exist and all that kind of stuff, but it's not that. But yeah, so we can see down here the DC operating point still 250 milliamps. It's still absorbing 625 milliwatts power, but now we get to see the current is explicitly flowing in a particular direction. So arguably a little bit more useful. Just depends on really what you care about. Okay. All right, so what I have shown you here thus far is effectively how to use LT Spice to check your answer for homework 1 part A, or homework 1 problem 1 part A, right? This didn't tell us how it got to this result in any way, shape, or form whatsoever, which is why I don't teach you guys about LT Spice in circuits 1, because we use web work for everything, and you could literally just simulate the circuit, make it figure out what the hell's going on, type that number into web work and call it a damn day and not have any clue about how to perform circuit analysis. But now that we're in circuits 2, we have a tool that lets us check our work, okay? That's what we're primarily going to use it for in this class. Supplementally, we will use it to aid in our design projects to make sure that things are behaving the way that we expect them to. So let's talk about how to get a Norton current, right? So we figured out our Thevenin voltage was 20 volts, no problem there. How do we measure Norton current? We could do a test source, not going to because I'm lazy. So Norton current by definition is the current flowing through the short circuit when we short circuit terminals A and B. So I'm just going to short A and B. So now A and B are short. If I run my simulation, arguably, I should now be able to figure out what my Norton current is. But we have a very small problem. We have a different problem because it's not showing me the thing that I want. It might be where my ground is. Let me fix this really quickly. Yeah, I want the transient on. There we go. All right. So the problem that I am experiencing is that I'm trying to find the current through a short circuit. And the way that LT Spice works is it only tells me the current through a component. And a wire is not a component. According to LT Spice, a wire is a node. So if we were going to use LT Spice to determine Norton current, we need to put something in there to give it something to measure the current flowing through. So I am going to choose a voltage source. And I'm going to be lazy and say that it's a 0 volt source. Effectively, this is a short circuit as a component. Rerun my simulation. And now I can see that my current is -2 amps flowing from B to A. So it would be +2 amps flowing from A to B. So now we verified our answer for part B. If I wanted to find my Thevenin equivalent resistance, well, it's just 20 volts divided by 2 amps is 10 ohms. All that kind of good stuff, right? So here we've simulated a DC circuit, okay? We'll do this periodically, but this isn't largely what we're going to use LT Spice for, because this is pretty straightforward and simple stuff. Instead, we are going to use LT Spice a lot to verify the behavior of our circuits in a transient condition. So I'm going to make just a quick and simple circuit here. I'm going to have, actually, let me draw the circuit that I'm going to simulate so that we can understand exactly what it is that we're doing. So let's say that I had the following circuit where I had a 10-volt source with a switch that's opening at T is equal to 0. And then a 5 ohm resistor. And just for the sake of argument, a giant 1 farad capacitor. Okay. And I wanted to determine the voltage drop across this capacitor as a function. Now, we couldn't get a more easy transient analysis problem to solve for here, right? So by inspection, we should easily be able to see that VC at 0 minus, which is going to be the same as VC at 0 plus, is 10 volts. VC at infinity is 0 volts. Our time constant tau is just R times C, is going to be 5 seconds. So VC as a function of time should look like 10e to the negative 0.2 t volts, because 1/5 is 0.2, right? I want us to simulate this circuit. We're going to simulate it for t greater than or equal to 0 plus, because for t less than 0 plus, it's just a DC circuit, and we already have done that. So that's boring. So let me connect my keyboard back to this bad boy. Yep. Here's my 10-volt source. Just going to leave this open circuited. I'm choosing to put ground at the bottom node. I usually put grounds to be the negative polarity terminal of capacitor voltages in any transient analysis problem. We'll talk about what to do when we have multiple capacitors once we get to covering transient analysis stuff again. If I'm not mistaken, this was supposed to be a 5 ohm resistor. This was supposed to be a 1 farad capacitor. I'm going to choose to label this top node as VC. And let's see, our time constant was 5 seconds, right? So we want this thing to decay all the way out to T is equal to infinity, which would be roughly 25 seconds. I'm going to give myself a little wiggle room, and we're going to run this simulation for 30 seconds. So it's nice and decayed. Yes, sir. 1 farad. Yep, just 1 farad. So edit my simulation command. Let's run it for 30 seconds. And when I click this node, I get nothing. Now, the problem that we have here is that we don't yet have a way to account for the initial voltage on the capacitor, okay? Excuse me. So what I'm gonna do is I'm gonna click on this .op button here and give LT Spice a command. So this brings up a menu. And the code that I'm going to type in is .IC. So this is initial condition. So I am telling LT Spice that one of my components is going to have either a voltage or a current across it at t is equal to 0 when the simulation starts. V, open parentheses, VC. So I'm telling LT Spice the voltage at node DC, which is the positive polarity terminal of my capacitor, started at 10 volts. I'm going to press OK, and I'm just going to drop this anywhere on my page. Okay. If I rerun this simulation, I now get a nice, neat exponentially decaying curve. I'm going to change the color of this because the green might be difficult for some folks to see. So we have a nice looking exponential decay here. Now what I'm going to do is I'm going to right click in my graph and I'm going to add a trace. So when this add traces menu is open, I can choose the voltage drop across the capacitor, the voltage at node 1, the current through the capacitor, current through the resistor, all that kind of stuff. Or I can just type in an expression here, which can be some algebraic combination of these things. And I can also just put in a mathematical function. So I'm going to put 10 times exp, open parentheses, negative 0.2 times the word time, which is my time variable in this thing, and press OK. And now let me change this to red so we can see it. Our red curve has completely overlapped our blue curve. So this is our analytical solution that we use circuit analysis to determine. This is what our simulation is giving us. And if the two curves completely overlap each other, that means that our analytical solution has to be correct because it agrees with our simulation, right? For a circuit this easy, that's boring. But for what we're going to be getting into, this is going to be in making sure that we're doing things correctly. It's not going to help us find errors by any stretch of the imagination, but it is going to let us know that errors exist somewhere in our solution. Yes, sir.
How do we get rid of trace?
So if you want to get rid of a trace with your mouse in the plot area, press the delete key, bringing up the scissors, and then just scissor over the thing at the top. Yep. All right, so we are out of time for today. Sorry, it took me 15 minutes to figure out how to get stuff on the projector, but once we got it going, I think it went okay. If you have any questions about anything, I'd be more than happy to answer them. If not, I will see you guys on Friday, where we'll start talking about new things. Yes.
What does it mean when the two curves overlap?
If the two curves completely overlap each other, it means that our simulation and our analytical solution agree on the same result, which means we did everything right. So if, for example, I put in here ten times exp negative 0.25 times time. Now my curves don't overlap, which means I must have made a mistake somewhere because they're not the same thing.